As we start topic 2 of chapter 3, we're going to be dealing with truth tables and equivalent statements. But I've put something here from math that you may or may not remember. And if we were to graph what is called a disjunction, or the OR statement, which is the inverted or the upside down caret, this is what it would look like. There's a break between them. This is a disjunction, and we'll be referring to this below. Now for the conjunction, this is an AND statement, and the symbol for AND is the caret. So again, conjunction, the caret, the AND as the connector, disjunction, an inverted caret, a V in a sense, and the word as a connector OR. So you'll need to read this, so let's pause while you read it, either from your textbook or here. So let's take it in parts. Truth values of component statements are used to find truth values of compound statements. To begin, we must decide on the truth value of the conjunction P, and notice we're using the word AND, Q, and the symbol for that AND, remember, is the caret. So this is the conjunction of P and Q. Now here it implies that the ideas of both P and Q are true. And they give this example. Monday immediately follows Sunday. That is a true statement. March immediately follows February. That is a true statement. On the other hand, the following statement is false. Even though part of the statement, Monday immediately follows Sunday, is true. So Monday immediately follows Sunday. This part is true. March immediately follows January is not true. So therefore this conjunction is false. In order for the conjunction to be true, both parts must be true. So for the statement, for the conjunction P and the caret Q to be true, both P and Q must be true. This results in a summarized by a table called a truth table, which shows truth values for P and Q for all possible combinations of truth values. For the component statement P and Q. Now remember, both of these must be true in order for this to be true. So we set up a little table. This is the truth table for this conjunction. Remember, this is the caret, and. So if they're both true, the statement is true. The component statement is true. If one is false, that is the Q, then it's false. If the P is false, then it's false. And of course, if both of them are false, then it's false. So this is the truth table and should be in your notes. You're going to be allowed to use your notes. Let's go on. So as we look at example 1, find the truth value of a conjunction. Now here we see let P represent 5 is greater than 3. Well, this is true. Let Q represent 6 is less than 0. That's not true. This is false. So find the truth value of this conjunction. Well, in order for this conjunction to be true, both must be true. It's obvious that they're not both true, so this is false. And if you went to the second row of the conjunction truth table, shows that is the case. Now they color this a little bit by saying that sometimes the connective but is used in a compound statement. He wants to go to the mountains, but she wants to go to the beach. So the but can be replaced with an and it therefore makes a conjunction. The truth table for the conjunction above would apply. Can these both be true? Now this would create maybe a family argument, but if he wants to go to the mountains, that would be a true statement, and she wants to go to the beach, that would be a true statement. Then the conjunction would be a true statement. All right, let's go on now to the disjunction. Here we're going to use the word or, where only one, but not or both, may be true, but at least part of it is true, then it is a true statement. So let's read this. So in ordinary language, they say the word or is ambiguous. The expression this or that can mean either this or that or both. This or that, but not both. So that's what ambiguous means. It has a variety of meanings. I will paint the wall or I will paint the ceiling, which means I will paint the wall or I will paint the ceiling or I will paint both. So here they're giving you the definition through examples of what disjunction means. That one may be true, or the other may be true, or both may be true in order for this to be true. And that's what we'll build toward. Continuing, it's I will wear my glasses or my contact lenses. Here, it will probably mean you're only going to wear one. To wear both of them, that would really ruin your eyesight. So, the symbol, the inverted caret, or the V, represents the first or described. That is, V, P, or Q means P or Q or both. That's the disjunction. And that's why the word ambiguous comes in here, from the Latin ambos, which means both. But notice, as we continue, we might call what is called the inclusive disjunction, or just the disjunction, in everyday language it often means just one of these items would be true. So look at the statement, I have a quarter, or I have a dime. Now what does that mean? That you would have perhaps a quarter or perhaps a dime, but not both, although it could mean both. But the only way this could be false is if you didn't have either of them. So in a disjunction, only one part of the conjunction, the compound statement, needs to be true. And the key word for expressing that, of course, is the word or. And the symbol for it is the inverted caret, or a V. So the disjunction of P inverted caret Q is false only if both components are false. So looking at the truth table for the disjunction, remember this is going to be the V here, or the inverted caret. If both statements are true, then it is true. If one is true, one false, it's true. One false, one true, it's true. The only way it's false is if both are false. So we're starting to accumulate our truth tables. And the shortened form of this, in order for a disjunction to be true, only one part of it needs to be true. In order for it to be false, both parts need to be false. So as we read it, let P represent 5 is greater than 3. Is this true? Yes. 6 is less than 0. Is this true? No. But only part of this needs to be true. Therefore, according to our table, this is true. Now, they're introducing these symbols here. The symbol greater than or equal to is read that way, while this symbol less than or equal to is read that way. And if A and B are real numbers, we're saying A is less than or equal to B. That is, A is less than B. Or A equals B. And we'll take a look at this table. So notice the statement, 8 is greater than or equal to 8. Part of it is true, because 8 equals 8. Now 3 is greater or equal to 1 is true because 3 is greater than 1. Part of it is true. Now -5 is less than or equal to -3. Again, it's true because part of it's true. And -4 is less than or equal to -4 is true because part of it is true. Okay, just to let you work with these signs a little. All right, we're now going into the concept of what is called negation. Negation is, in a sense, the opposite of something. If something's true, then the negation of it would be false. And this is written by the symbol, a little wavy line, which can be read negation or using the word not. So, truth table, a little short summary here. This is the statement. The negation of it is not P. This is true. The negation of it is false. This is false. The negation, or not false, is true. So something easy. Now in example 3, we start to put all of this stuff together. So we're saying that P is false and Q is true. And they're asking us this statement: the negation of P, or not P, and then in parentheses, Q, the inverted caret, or the not R, or negation of R, whether this is a true statement. Now, because this is an and here, both of these must be true in order for this to be true. We've proved that already. So what's the strategy of something like this? Well, if I were a student, I'd write it out, and then I would then work within the parentheses first. So we're saying that Q here is true. So I'm going to say that's true. And I see I left R off of there initially, but it's there. So R is false. So not R is going to be true. So we have here now the or statement that both of these are true. So we know that this part is true. Now we said P initially was false, but we're negating P. So the negation of P, or not P, will make this true. So we now have this as our final event, so to speak. This is a conjunction, this is an and both are true, so this statement is true. And they give you the details of it here as well. And this is a math class, so we want to deal with some mathematical statements. We can use truth tables to determine the truth values of compound mathematical statements. Now we do this in a math class normally, but here we're using this applied symbolic logic. Now to start us off in pieces, let's take a look at what they're saying. They're saying P represents 3 is greater than 2. Well, this is true. Q represents 5 is less than 4. That's false. And R represents 3 is less than 8. That's true. So if we keep this in our minds, it'll help us as we go to find these statements, whether they're going to be true or false. Now remember, the symbol for caret is the word and both must be true for that to be true. And the inverted caret is the symbol for or. This is the conjunction. This is the disjunction. Here only one part needs to be true, or both. But to be false, both must be false. All right, let's analyze. So as we look here at not P, P we said was true, so not P is going to be false. Now we said Q was false, so not false is true. And since this is a conjunction, in order for it to be true, they must both be true, so this ends up being false. And that is right down there. Now, we have to do what's in the parentheses first. P, we said, was true. Q, we said, was false. So, internally, is this true? Well, it's conjunction. Both must be true, so this is false. But now we are negating not false, so this is true. Once again, this was true, this was false. So this statement internally is false. But then when we negate or saying not false, it makes it true. All right, C. Now in letter C, we go to our little summary here. So P is true, so not P is false. And in conjunction, R is true. So here we have a false and a true. For a conjunction, this is going to be false. Now here, Q is false, so not false is true. And P is true, so not P is false. So this is a conjunction. They both have to be true, so this is both false. Now, we are asked, in disjunction, the inverted as an or, in order for this to be true, both of these must be true. I'm sorry, at least one of them must be true. And since they're both false, the overall results for this one is false. And it is in your textbook, and hopefully our description is helping. When a quantifier is used with a conjunction or a disjunction, we must be careful in determining the truth value, as shown in the following example. Well, we did that by looking at the mathematics of it, found out if that statement was true or false, and then identified it then as a true-false, and then applied it to our truth tables. Now, looking at example 5, we are to decide whether quantifiers statements are true or false. For we're looking at quantity here. So let's look at this one. Now, this is an and. So in order to prove this true, we have to find one value that makes both of these statements true. So we say x is less than 5 and x is greater than 2. Graph of this, notice that any number greater than 2 or less than 5 would make this statement true. And by the way, this is what a conjunction looks like. So this is a true statement. Now for number 2, or letter B here, they're saying that x is greater than 0. So if we graph that, it would look like so. And we're saying x is less than 1. So if we graph that, it looks like so. So, since it's an OR, everything would make these statements true. So this is a true statement. And by the way, this sort of represents a disjunction, but since they overlap, it looks like this. And this is the case where both are true. Letter C, for all real numbers x squared is always greater than 0. Well, as we look at that, if we square that, and the key here is all, we only have to find one example that would make this false, then it would be false, because they're giving the universal all. That's that wide paintbrush. So is there any real number? Now, if we had a negative number and we squared it, it would be greater than 0. If we had any positive number and we squared it, it would be greater than 0. But this is the tricky part. How about if you have the number 0 itself? If you squared 0, that's an unsigned number. Is that greater than 0? Well, 0 is not greater than 0. 0 equals 0. And there's only this one sign. Now, if it had this equal bar underneath it, that would be true. But since it's set up this way, this is false. And it's just that one narrow exception, that if the number was 0, if you square 0, it's 0. It's not greater than 0. All right, that was a little tricky. They give us a little aside here. Again, we're not going to do that. Now they are mentioning truth tables again. They're saying this is a good tool. Develop your truth table. Doesn't take too long. And then you can just pick out your answer from the table. Now, to develop mastery of this, as we are asked to construct a truth table, we want to know and clearly define what we're dealing with. Where we're saying a little later that P and Q are true, but right now we're looking at this particular statement. P is true, Q is true. This is an AND, where they both must be true for this to be true. And this is an OR. In order for this to be true, part of this must be true. It's false if both are false. So construct the truth table. And we see this down below. So let's take a moment to go over it. So as we start to list this, it's just going to list all the possible combinations of P and Q. So they could both be true. One could be true, one could be false. One's false, one's true, both false. Now, if we negate the P, then this will be false. This will be false. But if we negate P, the F will now be true, and this will now be true. So if we negate Q, jumping way over here, we see we have false, true, false, true. Now, we take our values as is shown, and we put them where if not P and Q, they had to both be true, but they're not both true, so this is false. They're not both true, this is false. Now we're negating this and negating this, so that would then be true. And then this last one, when they're both true with the negation, that is false. That may take more study, but looking at it carefully, we're now going to add our final column where we're looking at the event. And we see then false, true, true, true. So look in the first row of the final truth table above, which is this one, where both P and Q have truth values true. Read across the row to find the compound statement is false. Again, study and mastery. Textbook to study this. It's a little too detailed for me to go over it verbally with you, but again, it's laid out accurately. And they give you the values here. All right, let's go on to topic or example 9, using inductive reasoning. We worked on this a little earlier, but if you read through this, it comes up with the little chart right here that gives you, if you have one statement, you're going to have 2 rows. If you have 2 statements, you're going to have 4 rows. If you have 3 statements, you're going to have 8 rows. So the formula will be 2 to the n power. And that will be that. They're getting into truth tables big time. We're not going to get into that, and I'm not going to try to describe it. It's just too complicated. But again, looking at that, the circle number indicates the order in which the various columns of the truth table were found, and we have our formula. Okay, evaluate statements and De Morgan's law. Now here we say 2 statements are equivalent if they have the same truth value in every possible situation. And they'll give us some here on the next page. We are going to decide whether or not 2 statements are equivalent. Are the following 2 statements equivalent? Well, we construct truth tables, and looking at this in our textbook, we say that they are equivalent. And this is expressed as De Morgan's law for logical statements. So the negation of P or Q, and it's 3 little lines there, looks like the equivalent symbol, not P and not Q. Now notice here we have a and, here we have an or, here we have an and, here we have an or. So this is, I hope I said that right, this is the or, this is the and, this is the and, this is the or. So write this, or we should have that in our notes. This is De Morgan's law. So in applying it, let's see what we have here. Okay, in example 12, we're going to apply De Morgan's law. They're saying I got an A. We're going to say that is P. And I got a B. That is Q. Now this is an or statement. So this would be P inverted caret Q. Now the negation of that would be, you could put that in parentheses and negate that, which is what they have right here. Or you can convert it to, according to De Morgan's law, negate P, and now instead of an or, have an and, negate Q. And putting that into words, I didn't get an A, and I didn't get a B. In letter B, again, our first statement is a P, and our second statement is a Q, and it's an and, so we're going to use a caret. And then we will negate that, as they show here. And we said that is equivalent to the negation of P or the negation of Q. So the statement would be, she will try, or he won't succeed. And in the third one, they have it laid out. It's a little more complicated, but we see the negation of a negation. This is an or, this is an and it's equivalent to this. So eventually, they are negations of each other. Now in the text, they do go over, for further thought, the logic behind computers. You know, it's a binary system. It's either 0 or 1. And there are different little things that is challenging. This goes through some of it here to give you an idea of how things work. But I'm not a computer engineer. All right, let's go on to do some practice. If we have some time, we'll do some of these exercises here. Let's say 1 through 8 and see how we do.